Welcome to lecture 2, which is on developments in the surveying equipment. So, in this lecture you are going to learn many things like what is the historical background of the land surveying, how developments have taken place over a period of time in the surveying equipment world over, what are digital surveying equipment and what are their applications and advantages of digital surveying equipment. Now, if we look at the developments in surveying way back 14,000 BC, in Egypt the surveying began with the mapping of the land along the Nile river, which was primarily for the taxation purpose, and divisions were made because there was annual flood in the river. So, maybe to design flood protection measures. So, Egyptian surveyors relocated the land division measurements with the help of the ropes having knots, because that time there were no measuring devices. So, these measuring devices were the knots were tied in the long rope at regular interval, and these were laid down on the ground and distance was computed. Then for the construction of the Egyptian monuments, the use of surveying has expanded. Extensive use of surveying was done in construction of those monuments. Then later on the Greeks, they expanded the work which was done by the Egyptians and developed the geometry. So, the coordinate geometry, the trigonometry which we are using, actually these were developed during those times. And there was a development in the surveying instrument, and this instrument was called Diopter. It was like a level, so that we can find out the elevation difference also. Then Romans came forward and they developed surveying to create the roads, the infrastructure, aqueducts and land divisions in the area. They also developed several equipment like Groma has been used to determine the lines and the right angles. Libila was another instrument, A frame with a plumb bob, which was used for leveling purpose. Then Sorobates 20-minute straight edge with the oil in notch for leveling purpose. So, these were some of the devices which were developed by the Romans. Then in the Middle Age, further land divisions of the Romans continued in the Europe, and quadrants, which was a square brass frame which was developed by an Italian, and this has a graduated scale and we can measure the angles up to 90°. So, these are the developments which are taken place over a period of time, and measurements were taken with the help of these instruments to carry out the mapping of the land. Then in 18th and 19th century, development have taken place all around the world, because everyone thought that there is a need for mapping of the land surface, and there were marking land claims which were caused extensive survey, especially by the English people. And we can see that in 1785 the United States began extensive survey of public lands. Then in 1807 United States Geological Survey was founded and carry out the mapping for the control network of the area. So, that is how the surveying has developed in the whole globe. If you see the 20th century and beyond it, there was an increase in the land value, because the land was limited and everybody needs a piece of land for development. So, there was more and more need of surveyors, providing the training to the surveyors so that we can accurately map the land surface. So, educational requirements started in 1990, so that people are educated in this field, in this area. Then slowly we moved from conventional based devices to electronic based devices. They were developed. like positioning systems, GPS which we are using, electronic distance measuring devices, then construction machine control, the LiDAR scanning devices, they were all slowly developed then. Then we used geographical information system GIS in rebuilding the infrastructure. So, because we can store the database and we can update the maps easily in that. So, when the demand increases, there was a shortage of licensed professionals, and that was projected in the 21st century that we need more and more people who have good knowledge of surveying and mapping. If we look at the developments in the map making process, the first known map is the engraved on a hill piece, you can see on a stone. Then spherical astrolabe was developed to take the measurements. After that, the cross staff for taking the measurements of the star and the moon, etc. Then sextant was developed to measure the angles from different angles. Then after that, the manual technology was developed to create the maps from the data which we are capturing in the field. Then the magnetic technology came, where we are using the compass, etc., and so on for noting down the directions. Then mechanical technology was developed to prepare the maps, and then the optics came later. So, optics based instruments were developed, and we were able to see longer distance, longer observations from a point and note down the readings manually. Then photochemical technology came, where we started taking the aerial photographs from the balloon, hot air balloon, or from the space using the aeroplane. Then later on, the remote sensing technology, where we used satellite images, where the various satellites are launched to take the images, and these images were used to carry out the mapping directly. Then drone technology, because we require very high resolution photographs. So, these are taken from a low altitude. We require very frequent photography, then we use the drone technology. We require three-dimensional data, so we can collect the LiDAR data from the drone technology. So, all these technological developments have taken place in the field of map making, and our maps have become more and more smarter and more accurate. So, this technological development, if you see from industrial revolution to the electronics revolution. So, when industrial revolution came, it improved our surveying devices because we had advances in the available material. So, our material has become actually very light and non-breakable material. Then improvement in the tools, our tools have improved, they became lightweight, because transportation of these equipment, heavy equipment, was also a problem in the field. So, our equipment in the industrial age, they have become very compact, they have become lightweight, very easy to transport with a longer life. But when the electronics revolution came, lot of electronics have entered into those surveying and mapping devices, and we were able to measure the distances and angles which were done earlier manually, electronically, automatically. So, the instrument will keep a record of all that data, and we use the software actually to process the data. Then we have a satellite surveying, where we are using GPS to compute the coordinates, or we are using the digital data from the remote sensing satellites to carry out the mapping. Then we have the LiDAR surveying, where we can collect point cloud three-dimensional data with the help of the LiDAR technology. Then in the data processing also, because a lot of software came earlier, all the data processing was done manually, but today we have the data processing software. So, there are various softwares which are available for data processing, creating 3D maps or doing certain computational work. If I look at the technological development, how the technology has developed and mapping techniques have came. So from manual techniques, as you can see, we have gone to the magnetic, mechanical, optical based, photochemical, and now we are in the electronics era. So this is how the changes have taken place in the field of mapping and surveying also. Data acquisition platform. So today we have a very large number of data acquisition platform. We are when we are very close to the ground, so we are here with the electronic based equipment, maybe a scanner, maybe a GPS devices, maybe a total station devices, and we are covering a small area from this device. The second equipment today with us is the drone system, where we are mounting the camera systems, where we are mounting the LiDAR systems, and we are flying at a relatively lower altitude to collect the data of the earth surface. Then aerial photography. From aerial photograph, we cover a little larger area as compared to the drone photogrammetric techniques. And the last one is the satellite, which are flying at a much higher altitude, cover a very large area. So we have various platforms. So from each of the platforms, we are covering the ground area at different resolution, at different scale. We can integrate the data also from these platforms in order to have better and better mapping, in order to have the detailed information. We have very large number of equipment available today, and they are all digital in nature, they are all very user friendly, they are a smart equipment. So whether we are talking of GPR, ground penetrating radar, for taking the utility underground measurements, or LiDAR data, where we are collecting the 3D point cloud data, or we are using the geodetic GPS, where we are getting the coordinates to the millimeter accuracy, or we are using 3D scanner, we are scanning the whole environment from the ground surface. Total station, which gives lot of data, angular, elevation and distance measurements, or maybe the handheld GPS, which also gives us quite accurate data. So we have lot of devices available at our disposal to collect the data. Earlier, it was all paper based planning. We had to spread the paper map on a table, and we were reading those maps. We were trying to measure manually the distance or the area from these maps, and computing the elevations also by interpolation techniques. But we have shifted from this paper based planning to the modern approach, where we are collecting the data using the digital devices, digital equipment like total station and GPS, and we are using this data in computer, in a software, so that we can carry out a computer based planning. So not only we visualize the ground in 2 dimension, but we can visualize the ground in the 3rd dimension. We are measuring the angles from the devices. Earlier we were measuring with the transit theodolite, which has 20-second accuracy, but today we are measuring the equipment with the total station up to 1 second accuracy. So this is the transition which has taken place from manual approach, which is the transit theodolite, to the total station, where we have the electronic based device for measuring the angles. Then we are talking about measuring the elevations, the 3rd dimensions. We had auto levels, then we have digital levels, and we have the total station. We can measure the elevation from that also. So from digital level and total station, it is all in electronic based mode. We have the digital data, but auto levels we have to still manually note down the reading, but it is quite accurate as compared to our earlier dumpy level or tilting level. Once we measure the elevations, then we have to measure the distances also. So there are several methods of measuring the distances. direct method of measuring the distance. So, there are instruments which will directly give you the distance. Earlier method were pacing method, where with the help of the pace the person will walk down, and each pace is considered to be about 80 centimeter. We multiply by the number of paces, we get the distance. Then came the odometer, where this wheel, the circumference of the wheel, and we can find out how many rounds the wheel has taken and can determine the distance. Then chain surveying came. Tape still we are using for measuring the small distances, but the modern devices include electronic distance measuring device, which is shown over here, which can give you very long distance in one go. Then we have a total station, laser distance meter, which is shown at the bottom here, which can give you distance of 15 meter or 20 meter very easily with the help of this laser distance meter, and this is a replacement of the tape. Most of the people who deal with the mapping device, actually they have adopted this laser distance meter in the field, because there is no need to spread the tape. Then we have the laser scanner, where we can measure the distance up to kilometer long. So, this is how the technology has changed. From the small distances we have come to the longer distances, which could be more than a kilometer in one go. So, our approach has become very fast of measuring the distances. Then there are indirect method of measuring the distance, and these indirect method, when we were computing the distances, we were computing either using the trigonometry. We know in this particular figure, for example, this is a right angle. So, we were using trigonometry when we were doing triangulation, or we were doing trigonometrical leveling. So, with the help of the vertical angle and with the help of the height of the object, we can find out the distance between the object and the instrument. The other method was, we can use distance time relationship. Distance is equal to velocity into time. So, this relationship has also been used actually to compute the distances. We can also find out the distance from the coordinates. For example, the GPS will give us coordinates, and using these coordinates, x and y coordinates, we can determine the distance between the 2 points if we know their coordinates. So, this is how the technology has changed from conventional method of measuring the distance to the modern approach. Electronic distance measuring devices, which were developed after World War II in the advances in the radar, they have actually revolutionized the surveying and the mapping job, because they are able to give us very long distance. So, there were broadly two types of EDMs which are developed: microwave based, and the other one which were actually infrared based. So, microwave based were giving us the range of 20 to 50 kilometer, very long range, and the other one will giving 3 to 20 kilometer range. So, we are using in engineering survey purpose, we are most of the time we are using the medium range devices, 3 to 20 kilometer range, and we are getting very high accuracy from these devices in measuring the distances. Then electronic theodolite, or what we call it the total station, also is a wonderful equipment when we are doing surveying, land surveying and mapping, because this can measure horizontal angle, vertical angle and slope distances. So, these are the measurements which we are directly taking from these devices, but it can compute. There is a small program, and this program helps us in computing the horizontal distance, the vertical distance, the azimuth of the line and x, y, z coordinates of the point. So, we can compute lot of data once we take these measurements using the capabilities of the data processing software available with the total station. Along with the EDM or total station, we are using prisms. Here you can see the normal prism on my left and the other prism, which is called a 360-degree prism. So, these are the two kinds of prisms which we are using, and these prisms are made from the cube glass corners, and also they have the property of the reflecting rays back precisely in the same direction as the incident ray, and also they can be mounted on a survey pole or on a tripod. So, advantage of this 360-degree, which is on my right, the advantage of this particular prism is that the ray can strike anywhere on this prism and reflect back to the same point from where it has come. So, we keep the prism at a point whose coordinates are to be determined or distance is to be determined, and at the other point we are keeping EDM or the total station, and then we are taking the measurements using the capabilities of the prism. So, this is how we work with the total station. The person is taking the observation with the total station after setting it up at a point, and at the other end we are keeping the prism. So, we have to move the prism quite frequently in order to take large number of measurements with the total station. Very simple principle is used whether we are using total station or EDM or maybe the GPS technology. We are using distance is equal to velocity into time relationship. So, here in case of the EDM or total station, it is sending the beam to the reflector, and from the reflector it is coming back and the phase difference is measured. So, it is measuring the time phase between the incident and the reflected spectrum, and it is computing the distance. So, now we are also taking observation in the laser mode. So, in the laser mode there is no need actually to keep the prism. So, there could be locations on the ground where it is not possible to keep the prism. So, here we can use the capabilities of the instrument in the laser mode. So, it also provide us flexibility to work in the night hours, because we can very easily see the laser beams. It is also very fast method of data collection, because you do not have to move the prism from one point to another. So, your speed of data collection becomes much faster, and the best advantage is that one person can finish the entire survey work quickly. Then there is a further improvement development. This is the robotic total station. That means that you do not have to stand near the equipment, the instrument will track your movement. That means you are simply carrying the prism pole, and the prism pole has a sensor attached to it, and the sensor in the equipment and the prism pole, they are communicating with each other. So, as you are moving with the prism pole, the instrument is tracking the movement. So, for example, this is a prism pole and instrument is tracking the movement of this prism pole, and you can trigger the instrument with the help of the remote control, and the instrument will record the data of that particular point. So, this is again a very fast method of data collection, and you require one person to operate the entire devices. So, if we look at the electronic devices, electronic equipment which are available to us nowadays for collecting the data, they save lot of time, they ease in work, they increase our accuracy, they are very compact in design, lightweight, and there is no actually chance of reading or recording error, which was quite obvious earlier. And you can use the capabilities of the software to process the data very fast. You have increased range of taking the measurements, and you have the facilities of taking the night observation, and the other advantage is all weather working capability. You can work in all weather conditions using these devices. Then the GPS came as a mapping system. So, this is a worldwide radio navigation system which allows us to determine the exact position and time. So, in surveying and mapping, we are using only the three-dimensional position, and the advantage of this device is that you can take the data, collect the data in all weather condition anywhere in the world. So, this will provide us very highly accurate positional data, three-dimensional data, which we can use for mapping purpose. And also we are using the signals from the GPS satellites. So, minimum 4 satellites are to be tracked in order to get the accurate position. There are large number of navigational GPS or handheld GPS which are available in the market. So, These will give us quite good accuracy, sub-meter accuracy if we are using for a navigational purpose. Suppose we have to plan a 30-kilometer road. So, this navigational GPS will give us fairly good accuracy to carry out the mapping of 30-kilometer road. But if we want very precise observation in millimeter, we have to design the span of a bridge, we want to carry out very accurate mapping, then we have to go a system like this, which is called geodetic GPS, where we have controller and receiver separately, and we can take the observations very precisely. So, the mapping the land features GPS have been used very frequently because it will give me latitude, longitude and elevation with respect to WGS 84 datum, World Geodetic System 84 datum. What it requires? It requires clear visibility to the sky so that the signals are received to the instrument. So, ultimately it is a very cost effective technology and it saves lot of manpower in the field because one person can finish the entire job in the shortest possible time. So, this is the GPS survey work which is carried out in the field by a single person along a given corridor. So, these are the satellites and the signals are received from these satellites to carry out the mapping. If the area covered is very large, then probably it's physically it is not possible to carry out the device from one point to another point. So, this device can also be mounted on the vehicle. As you can see here, the antenna is mounted on the top of the vehicle and receiver is also on the gate of that, on the door of the car. So, you are moving the vehicle and at the same time when you are in moving mode, you are collecting the GPS data. Many times we have the problem of the signals from the GPS satellites, or we have the problems of the horizontal visibility because of the obstructions which are coming on the way to actually collect the data. So, in that case what we are doing is we are using a combination of the two devices where GPS and total stations both are combined together, and that what we call it the smart station. So, we are using the capabilities of GPS as well as total station in the field. So, instead of carrying two instruments, we carry one single instrument and we do not have to wait for the satellite signals. In that case, we will use the capability of the total station, but if we have the horizontal obstruction, we will take advantage of the GPS in that case. So, our mapping becomes much faster. Then we have for underground utility mapping, we have an instrument which we call GPR, ground penetrating radar, very useful nowadays in a smart city application. Also this underground utility mapping has become very important. It has become almost it's a prerequisite for that. So, for this utility mapping, this instrument is a wonderful instrument which is called a non-destructive method of mapping the underground utility feature. So, in this instrument we have a transmitter and a receiver here which will transmit the radio signals to the ground, and on the display we can see the reflected signals which are coming from the ground. So, there are very large number of application of this apart from the underground utility mapping. We can do it for a hydrogeological investigation, we can find out the groundwater level, we can also find out what are the buried structures including the reinforced bar, cavities, tombs, archaeological artifacts, etc. So, this instrument gives us a capability to see what is below the ground. The next important equipment is terrestrial laser scanner for 3D survey work. We can mount it on a tripod and cover a very large area, up to kilometer long area if the visibility is there. It collects 3D data, it has a greater range of observation, it is automated data collection approach, and it provides point cloud data for 3D representation of the object. So, this instrument TLS has also given us lot of freedom actually to collect large amount of data in the shortest possible time. And if our area is further large, then in that case we are using the mobile mapping system, where we can mount all these systems on a moving vehicle. So, you can see here on the vehicle we have mounted a camera, we have mounted the GPS, we have mounted the laser scanner, and we can get the output in the form of the image, in the point cloud data, in the form of the three-dimensional coordinate. So, this is a very useful system, mobile mapping system, to collect the data for a large area. There are again various applications of these area, because the camera can collect 360-degree data in all the direction, forward, backward, left and right. So, you can cover the panoramic view of the entire area from one single spot. That is the greatest advantage of this. And the other advantage is that from a distance you are carrying out the mapping. So, you are not going to those fragile sites physically for carrying out the mapping. The next technology is the LiDAR surveying technology, which you will learn more in this particular program in subsequent lectures. But it was developed, it is not a new technology, it was developed in 1960, but at that time the LiDAR technology was not appreciated much. But nowadays we are using it for various applications, because we can get X, Y and Z position of the each return to the ground, and we can use actually this data to create three-dimensional view of the terrain of the ground. So, this is for example the first LiDAR data which was taken in 1999, and we can see the even the height of the buildings we can see. So, we can create a digital surface model actually from this data. On my right is the LiDAR data for a forested area. Here we can actually see the height of the forest if we blow it up this particular area. Then in the drone technology, which is also called unmanned aerial vehicle, no pilot is required. You can control the movement from the ground and can take the images from the camera or point cloud data from the LiDAR sensor. So, advantage is that we can carry out the mapping in dangerous and difficult area. So, this is one of the cost effective methods while we are collecting the data for mapping purpose. So, this is for example the topographical mapping which has been carried out from the drone survey. This is the 3D model have been created there. On this area you can see the yellow lines with the contour lines. So, we can very easily carry out topographic mapping, and you can update the new features at regular interval. There are some other mapping techniques also, aerial photographs which are used, satellite images, and we can create different kind of maps from the data in GIS environment. These are some of the suggested readings for this particular lecture. Thank you very much.